The second part of this is to talk about electronic components that you might see. And there's a lot of different components out there, and there's a lot of different things you might find on schematics. And the schematics we're going to go into more next lecture, so just kind of bear with me through this while I talk about schematics. But some of these components are also important to think about how we can damage them. We can either damage them mechanically, or we can damage them by what we call ESD, or electrostatic discharge. And for those of you that may not be exactly aware of what that is, whenever we all know what it is, because when it gets cold, or we rub, you know, we're walking across carpet, or we pet our cats, or whatever it is, and then you go pet metal, or you go touch metal, that you end up getting a shock to yourself. And as we all know what that feels like, it's not fun, but this can actually, the same thing can happen whenever you touch electronics after you have built up charge on yourself. And it's really important to be aware of this happening when you're working with electronics. And I would say, just also a side note here, even though I didn't see it in the lecture, whenever I handle a printed circuit board, I never just put my hand over the top of it. I always lift it up from the sides. That way I'm not putting my hand across anything on the top. You can still actually cause problems with it from the side, but it's just a better way to handle it. But for now, we're going to talk about some of these components and how to sort of mitigate some of the ESD events from happening. All right, here we go. So we're going to be talking today about resistors, capacitors, inductors, diodes, and as well as interface components. Some of these are often called passive components, and then we have other types, integrated circuits and different things that are more active. So, but we're going to start off with these. These are the basic ones. Go ahead.
The main difference between a passive component and an active component is the ability for it to amplify circuits, amplify voltages, currents, etc., so on and so forth. So all of these components, all they do is consume power.
Great point. All right, here we go. So resist. Go ahead. Okay. So so we're going to start off with the most basic device. So these are resistors, and as I mentioned before, resistors basically resist current. So whenever you insert them into a circuit, they will cause the current to decrease, as well as also resistors can just be like really long wires too. So that's always important to think about as well. Anyway, so the schematic representation of it is up to the right. Apparently in Europe, that's what it looks like. I didn't realize there was a distinction. I've seen it in both of these. Typically, the one on the right where it says USA and Japan, that's typically the way that I've seen it on a schematic before. So just be aware of that. And then also the values are specified in ohms, as we mentioned before. And then again, kilo ohms is 10 to the 3, and then mega ohms is 10 to the 6. So also important is that the value, all of the resistors have many different values, and they're marked with the value using this color code. And you can see here that 0 corresponds, it's black, and then 1 is brown, and then orange, red, yellow, green, blue, violet, gray, and white. And then this is referring to different tolerances. So if I have a resistor that is like 100 ohms, but it's 5%, then that means the actual resistor value, if I were to pick it up and measure it with the multimeter, can be plus or minus 5% of that value. And then the same thing with the 10%, but you can also, if your circuit needs to have a greater precision, which depending on what it is, it might need, you can go down to 1% or 0.1%. So they just cost more money or whatever. Also, just be aware that there are sort of standard values that you can order with resistors. So whenever you're like calculating a value in a circuit and you're like, I need this value, and you go look at it from a vendor, it may not be the exact one, and you might have to start like putting some things in series or parallels to get the exact value you need depending on what it is. And this little saying underneath here is just a way that you can try to remember all of these colors just off the top of your head. And apparently it's big bears run over your gladiola bed vexing garden worms. And I don't know, that's a new one for me. So that's something that's, it's pretty memorable actually. So I might take it on here to use that. Anyway, whenever you pick up a resistor, it's gonna, this is what we call a through hole component, and it's also an axial resistor. But anyway, there's gonna be some different color bands, and this is consistent across all through hole components. So there'll be a first digit, a second digit. If it's a precision resistor, there might be a third digit, and then there's gonna be a multiplier. And so if I were to look here, the first digit is blue, so that's 6. And then this is orange, so it's 62. And then this multiplier, I think is red. It might be orange. I don't know what it is, but let's just say it's red. Then it's going to be 62 times 10 to the 3. That's how that would be the value for it. Okay, and then the tolerance is usually the 5 or 10%, depending on what the color is. And the quality, I'll have to look at one to actually get a feel for that. But the main points I've just told you about is how do you read that. So if you pick one up and you're like, I can't quite remember what it is, you could always get your meter out and measure the resistance, and then you'll get the value, and then you can confirm what it is. But you have to remember those tolerances in there.
Yeah, and one thing I want to add here is later in semester 2, you guys are going to be working with surface mount resistors. And they actually have a slightly different way of reading resistors on them. We will be going over that material once again whenever you get to that material, but very briefly, you usually will get a numeric code, number code written on the resistor that will correspond to what that resistor value actually is.
Yes. All right. And also important are is the power rating. So as I mentioned before, we have a resistance, you'll have a current that's running through your circuit, that's going to run through your resistor. And if you multiply that current by the resistance, then you'll get a voltage. And then you can take that and you can multiply times your current, or one of those other forms of the power laws that we were talking about, and you can get what power is going to be taken on by your resistor. And with that, you need to make sure you pick the right resistor for the power that is going to be running through your resistor, or else it will burn up or some other failure mode that we really don't want to deal with. They can get very hot. So, commonly available is 1/8 watt or 1/4 watt or 1/2 watt, 1 and 2 watts. And then there's also much higher powers available. Just depends on the need. So just take a look at that. And then this will also change significantly with the surface mount or resistors that we were talking about. So be very aware of this. It's really important. And just down here, just looking at these two, I can tell you that these blue, if you do see like a blue resistor like this, normally I think that's a 5 or 1% tolerance. And then these typically, the beige ones typically are the higher tolerances, as well as you can see that there's like sort of an extra band on the blue one for the precision that I was talking about. Okay, so resistor handling and installation. So resistors are not polarized, meaning that you can put them in any orientation, and they may be installed in either direction. They are generally not susceptible to ESD or electrostatic discharge. That's what the ESD, when you see it, that's what it stands for. So special precautions are not really required. And the biggest kind of concern with them typically is the mechanical stress due to lead bending. And so like if you keep inserting this and into your circuit and you're like, that's not right, and then you like bend the leads multiple times, eventually the leads will crack. So just be aware of that. It's always great to have kind of a test set of resistors or something you might insert, and then whenever you want to like permanently insert them, then I would just get a new one because they're super cheap. And normally you'll have like 100 of them if you order them from DigiKey or something. All right, so capacitors. These guys are typically used to store charge as well as used for signal filtering. I'm not going to get into the details of that. but you'll see them for both of those applications. Oftentimes when it comes to integrated circuits, like what we're going to be using, they're typically used for filtering. And the values typically are specified in farads. So microfarads is very common, or picofarads. Again, microfarad is 10 to the minus 6, and pico is 10 to the minus 12. And these are marked with an actual value or numeric code. Unfortunately, nobody whoever, all the different vendors of capacitors have not made a great standard like they did for resistors, which I'm very sad about. And so it's always a hassle to pick up a capacitor and figure out what the value is. And multimeters are oftentimes not accurate enough to really give you a proper value. So if you get some capacitors, I would recommend always saving the bag that has the part number so you can go back and look at what it actually is. Some of these guys are polarized. So that means that the orientation does matter. So I just want to say real quick at the top, whenever you look at this particular schematic symbol for it, this is a non-polarized capacitor. But whenever I come over here and look at these that have this like curve, the semicircle thing, that's usually an indication of it is polarized, but really the true indicator will be when it has this plus. And hopefully on your board, if you were to do a board layout or your schematic, that you make sure to indicate that these things are polarized in your schematic, and you indicate the positive direction. And this means that whenever you plug this in, you should always put the positive lead with the positive voltage on the board, and then the other side should be towards the negative direction, typically, or ground. You'll see that. But not all capacitors are created equal, nor are they all polarized. So some of them are not. So the most, I'm not going to go through all the details, but very common are the ceramic capacitors. Those are also often used for filtering, and they're probably the most standard type. And then at the bottom, all of these, I want to point out that the tantalum and the electrolytics are polarized. And you can see there's like a little plus sign here. You can, if you actually look at these electrolytics, you'll see like a minus or a plus, whatever. And if you look at it and it's confusing to you, then go look at the data sheet and make sure you understand what the proper orientation is. Don't just make an assumption here about these guys. So these are just different types that you might see.
One trick I've seen that some capacitor manufacturers will do is they'll for the like the aluminum electrolytics that you see on here, they'll actually paint the negative side with a solid band of color like white or black. I'll see that happen fairly often too.
Yes. All right. Again, capacitor ratings. It says here physical size of capacitors are related to voltage handling ability, working voltage. So I would say that sometimes they're rated off of the actual capacitance value. So larger capacitors will also be larger than others. Again, look at a data sheet. But important point to this is not only are some of them polarized, but all of them have a working voltage. So whenever you are looking at what capacitor should I use, oh, this is requiring to, just have a 1 microfarad capacitor, and you need to go to that data sheet and actually look and make sure that that capacitor is rated for that voltage. And ideally, I like to have at least 2 times the voltage of whatever your maximum voltage you're going to be working with on a board. So if you're working with like a, something that's a 12-volt system, you can find capacitors that are rated for 25 volts or so forth. Yeah. I'll also say that some of these guys, they have a bias in them that depending on what voltage they're operated at, it may actually increase or decrease it'll never be increased above whatever the actual value is, but it may decrease based on the voltage that's applied. So just another important point. And that's really important with the surface mount components more than the through-hole ones. The temperature rating is also important. You might not be able to get the same capacitance value at different, if you're operating in a cold environment or a really hot environment. This is very relevant to ballooning because you might see a wide range of temperatures as you're going through the troposphere. And the temperature coefficients depends on dielectric material. So those are all really great things to think about. Somebody asked a question.
Yeah, someone asked a question, but it was Anna answered it. But yeah, DC stands for direct current. and the arrow usually is the direction of the current that it flows. The other thing I wanted to talk about here real quick regarding the capacitor ratings, Jill just talked a bit about how you always want to pick capacitors that are double or sometimes even more the actual value. And I want to tell you a little bit on the reason why is you might think, we're just working with DC voltages all the time, but the reality is DC is really rare to actually see, and everything's not truly DC. Like whenever you turn on or turn off something, there's going to be a surge of current, a surge of power, and that in that moment, it actually acts like AC, and the voltage will actually be higher, and you'll spike, and you can damage or lose your capacitors during that power on cycle. So it is actually very important that you do pick capacitors that are above the rating that you would expect because of those initial power on spikes.
Yeah, that's a great point. And in particular, this can happen anytime you turn a power supply on, but also in particular if you have any kind of motors or anything that will, typically those things have what we call an inrush current. So they can definitely cause some damage if your system is not robust enough to handle that. Okay, so again, we're talking about the polarization. I'm just going to re-emphasize it. Install it in the right direction. If it is polarized, it will definitely cause damage to your entire circuit, and it might release the sacred smoke that we mentioned earlier. It's not a good thing. This again is pointing out the electrolytic and the tantalums are polarized, and then it says here that they're not generally susceptible to ESD, and then again the same problem with the resistors with the mechanical stress from the leads. This is definitely true with the capacitors. I feel like they're even weaker than the resistors in many cases. So just be aware of all of that. Again, these things are normally cheap. They come in a lot. So when you order them, you'll have a package of them. Just switch it out. All right, so inductors. Their values are specified in henries, millihenries, microhenries, and this is a coil of wire that may be wound on a core of air or other non-magnetic material, or on a magnetic core such as iron powder or ferrite. In general, these store energy in a magnetic field when current flows through it, and it opposes any changes in current. And I've most often used them for filtering circuits, but they can also, two coils magnetically coupled, form a transformer. And these are some different types that you may see. I have to say that typically when I use them, it might be like the ferrite core, with the being wrapped around the core, or I've seen them in smaller packages meant for to be mounted on a printed circuit board. So yeah, but if you're using it for filtering, you should definitely have a good understanding of what frequencies they're filtering and how that works. So keep
real quick, there is one question
Yeah.
from Jamel Mohammed. I'm sorry, I'm bad at pronouncing names, and I apologize for it. I have a question. I have a couple of students in the OEO team that are taking the first physics course. They will not learn about voltage, resistance, current, electric power until next semester. Other than the Intro to Physics textbooks, is there any books or websites you guys would suggest to teaching them these terms in the simplest of terms? I actually don't know what would be a good website right off the top of my head, but there are quite a number of resources out there. Do you have any books or suggestions?
I can certainly, I'm going to take a note to get back with you on it. I often will simply type these things into Google, of course, and there's so many great tutorials out there, but let me just make a note and let me get back with you on that.
Yeah.
I mean, there is.
Hey, Jill.
Yes.
The Spark Fund is a good tutorial place. So if they go to tutorial sections in Spark Fund, I mean, they talk about stuff that is geared towards even elementary sometimes. But I know they got like how to use a multimeter tutorials and voltage divider tutorials and that kind of stuff. That could be a potential place to look.
Yeah.
That's a great recommendation. That's a great recommendation. Yes, Spark Fund. It's just sparkfund.com, and they also have amazing little development boards that you can order, and a lot of robotics development tools as well. It's a great resource.
Thank you, Anna. Thank you.
Yeah, and I was also going to say that that as you pointed out, the introductory physics course books, the second semester will talk about all this stuff in the basic information. So all the basic concepts are there, so they can just read ahead.
And if you guys if any of the students ever do run into some physics questions and stuff like that, don't hesitate to, send one of us an email. We'll do our best to reply and give you answer the questions to the best of our ability.
Yes, yeah. All right, we're gonna move on to inductor ratings. Again, all of these components have ratings for current and power, and those need to be, understood what it is, as well as this is also bringing up an important part about temperature dependence. So the handling and installation, they're not polarized and may be installed in either direction, but I would say that I was certainly working with some of these PCB mounted ones from Coilcraft and for particular filtering, and they had a recommended orientation. So just because they're not polarized, there might be a preferred direction. Again, look at the data sheet, get with the vendor and find out. They're not susceptible to ESD, but the same mechanical stresses can occur here, and inductors in timing or frequency determining circuits should be installed in mechanically rigid fashion. So just think about that.
One thing I will say regarding inductors is, especially if you ever have an old circuit, they do degrade over time, and they can fail just from like the insulation and stuff like that just going away. So that is something to keep in mind if you ever are trying to have a long-term lasting electronic device.
Good point. All right, so diodes. So these are very common as well, and it's important to understand how they work. So as mentioned here, most modern diodes are semiconductor devices, and they're considered passive since they do not contribute any amplification or gain to the circuit, like Josh mentioned earlier. So so when I think about a diode, I think that they are like gates, and gates that open only in one direction. So in one direction, it allows current to flow, but in another direction, it stops current. So it's kind of like a one-way gate. And in the center here, I'm just going to go over this. This is the schematic symbol for it. And you can see that there's something called the cathode and something called the anode. And so this is when this device is hooked up with the positive side connected to the anode and the negative side connected to the cathode, and current is flowing through the circuit. That symbol that's wrong. Yeah, I'm sorry. Hold on one second here. I feel like the cathode and the anode are backward. Yeah. So excuse our presentation. So I'm gonna check on this and fix the presentation before we upload it. Let me just make a note real quick.
I'm also taking notes on like small typos and stuff like that for here.
Okay. Yeah. So.
It's only been this way for 15 years.
As you can see, it's very easy to mix up the cathode and anode.
Yeah. So the cathode is normally with a negative. Like I typically think of this big line as a negative, and then the anode is the one that doesn't have the big line that looks like a big negative. So that's how I typically look at this. We will fix this. But the point being is that whenever you have the anode connected to the positive side of the circuit, cathode hooked to the negative side, current is going to flow through it. And then if you put it in backwards, current will not flow through it. It's not like, though, the capacitors where if you install it backwards, you're going to have a catastrophic failure. It's not that. The device is supposed to work like this. And then this is whenever you see this one to the left, and you see these little arrows shooting out of it, that's typically a light emitting diode. So this is the LEDs that we see everywhere in our lives and on our phone and everything like that. That's the symbol for it. And it's just simply a diode, but when current flows through that device, light is emitted. And then this is a Zener diode, which is a different type that
real quick.
Yeah.
One thing I did want to add here, for those students who might have some difficulty like conceptualizing it, another way of looking at a diode is also like a waterfall, where you have a lot of water up front where it has like a lot of potential, and it crashes down to the bottom side where you lose all of that energy, and you can't just send water right back up the waterfall without additional help. So it works a lot like that in that concept.
Yeah,
Is
that's,
that to say that if you had enough power going in the other direction, then it wouldn't block it?
well, that's a good point, and we're going to get to some of the specifications.
Yeah.
Yeah. So just real quick, the different, there's different types again. They're made of different semiconductor materials that like might give off a different light or have certain properties of how like fast it might switch on or off and different things. This rectifier diode is typically like a pretty standard one that you might see in circuits that I would often use. This is the LED right here, the light emitting diode. Back to the anode and cathode, these things are typically marked in some way, either by the lead length or by a marking on the device itself to indicate the anode or cathode. Again, I would go to the data sheet and take a look at it, but I believe like with this rectifier diode, that's typically the negative side and this is the positive side. And then with the LEDs, there's typically one of the leads that will be longer than the other. And I want to say it's the anode that's longer, but I'm not sure all the time. And then like I know this like gallium arsenide type is typically like I believe like a blue LED, different colors. Anyway, that's the basics of that, what you might see. And then back to your question, there are different ratings with it to just keep in mind. Peak and burst voltage would be, you know, the maximum, like we said, you can put this in backwards or you can have the negative voltage, but there is a maximum to that before the device will break down. So you definitely don't want to exceed that if you're using it in that way. And then the forward current is the amount of current it takes in order for it to be, I think, like saturated, or the for example, for LEDs, like for the light to emit from it, I might be saying that wrong. And then the forward drop is also important as to once you have a specific current flowing through it, then there will be a voltage drop across that component. And typically, I can tell you that just for like normal diodes, that is 0.7 volts. So if you put a diode in, say, the great way to use diodes often is for circuit protection. So you have a battery coming in and you want to make sure that somebody doesn't accidentally hook it up backwards. So you could put a diode in line with one of the positive lines. And then if somebody hooked it up backwards, it would cause an open circuit. But the problem with that is say you have a 12-volt battery and then you put the diode in there when current is running in the right direction, that you're going to get a 0.7 voltage drop. So that means that you're going to get 12 volts minus 0.7 volts to your circuit. So it's just important to think of. So ideally, you want a little bit extra battery voltage, and then you can use this device to prevent somebody from plugging it in backwards, which is amazing. So important.
It saved many of an electronic.
Yes, yes, it's really important. Yeah, it's a good idea. Okay. The handling, you know, they are polarized. Again, it's not catastrophic failure if you do put it in backwards, but it won't work if you don't put it in right. They're modestly susceptible to ESD damage. And then again, these look like resistors at the end of the day, and so they have the same mechanical stresses as before.
And before we move on out of diodes, Anna did have one nice little tidbit for trying to remember
Okay.
which one's the anode and which one's the cathode. Okay. Her mnemonic is, hint to remember it, diode ends, arrow equals an anode.
Okay. Yes. So I was right with this, with the labels on here being incorrect. Yes. Okay. So now we're going to get into interface components. And so this is two different types of common plug styles that you probably have seen if you've like connected any electronic device to a wall plug or something like that. And I'm not going to get into too many details of these. I think we all know them. Although I would say if you do have power on this RCA plug, that just be aware that that voltage, the positive voltage, if it's on the tip, it's just hanging out. So if that thing accidentally touches ground or something like that, then you can certainly have problems. And truthfully, with all of these things, you know, if these somehow it comes into contact with a piece of metal across it, and you've got a ground and a voltage touching, you're gonna end up with some problem there. So just be aware with those things. And we're gonna get into active components here. So talk about transistors and integrated circuits, or ICs.
And just as a reminder from earlier, we were talking about passive components where they don't consume power. These will, you know, typically amplify voltage or current or some other aspect of the electronic circuit.
Yep. Okay, so let's just start with transistors. So I think of transistors as I think of basically like a switch. And so they're, in general, 3-terminal devices manufactured in a variety of packages and styles. Again, learning something new tonight. This was the very first transistor, so that's kind of interesting. These are the different types of signal or schematic types that you'll see for it. I can tell you that the first 2 are bipolar technology, and then the last 4 of them are field effect transistors, or FETs, we call them. So most often you might see a MOSFET. So one of them is like a BJT, and then the other is like a MOSFET is typically. And then you sort of have a couple different types. I think we're going to go over it more into detail here, yes. So different type, the top section, this is the bipolar junction transistor, and then these are the FET, field effect transistors at the bottom. They're used for different types of things. The BJT, as we call it at the top, is typically a current-driven device, and then the FETs are voltage-driven devices. So important to, you know, if you do start taking a look at these and trying to figure out which one to use in your application, certainly look at this on the internet. There's so many tutorials on this on the internet. But in general, they also are named a little bit differently, their terminals, and I'm just going to go over them briefly. So you've got the base emitter, and the base is this one coming off in the center, and then the bottom is typically the emitter, and then the top is collector. And the way that this typically works is you have you apply voltage across the base to the emitter ground, and then basically what it does is it will short circuit. And there's a linear effect that happens with current, so it depends, but eventually if you saturate it, that the collector will be tied electrically to the emitter, and current will flow across those. And then the same thing basically is a similar concept with the field effect transistors, where you apply voltage at the gate and then across the gate to source, and then you eventually get sort of a short circuit situation happening across between the drain and the source. So if you are driving a signal that you want to turn on or something, then these devices where you're basically controlling that signal through the base or the gate, and then it'll turn on. Trying to think what other important aspects here to talk. As far as just so you know, the BJTs typically have 2 different. They have like a N doping and then a P electrons and holes, which is based off the N and P working. They work a little bit different, but anyway, the NPN, I typically look at this and say not pointing in. That's how I understand the NPN, and the PNP is the one that does point in. So I'm gonna move on. The transistors are polarized, must be installed in the correct orientation, and then they're modestly susceptible to ESD, so definitely need to take ESD precautions here. And then apparently the MOSFETs are very susceptible to ESD. So, and then again, with all of these IC components, there's mechanical stress as well, so swap them out if they look bent really bad and you want to use them for a final configuration. And then we get to integrated circuits, which are multi-terminal devices that provide an array of functions and applications. Yeah, and far too numerous to list here. I agree with that statement. So on this board, the outside of it, what all of this is mounted on is called a PCB, or a printed circuit board. And then these black devices here that you see are all integrated circuits, and they all have an individual function that they do different things with. And then you can also see on here, just to point out, some resistors. I see these orange things are capacitors. This is a different type of capacitor. That looks like a 10 ohm capacitor to me. And then we have connectors here. that, you know, we can bring wires off the board. So this is kind of a standard, and then this is a potentiometer over here, which is a different type of device. So just to kind of show you all the different types of things that are on here. The pin identification and numbering convention is really important. This is probably the most important thing, other than knowing the function of the integrated circuit, is where the pin 1 indicator is. So there are typically, if you have what we call this, this is a through-hole component, and there is, it's hard to see on here, but there is normally like an indentation on the black part of this part. It kind of dips down, or you might see some kind of silkscreen overlay or some kind of indication should be on that part for pin 1. If you cannot find it, then I would go back to the data sheet. Fortunately, with these things, I would say that this part number is the LM324N. So if I were to look at that on the internet right now, I should be able to come up with a data sheet for this, and it should very clearly tell me where pin 1 is on the data sheet. Typically, it's right here though. This bottom stuff, bottom number is typically like a lot code or something. So it's a little less important unless you're like gonna fly it on a spacecraft where you have to keep track of lot numbers, and it's very complicated. In general, try to go to type in one of these numbers into the internet. Now, there's also like a notch, or there might be a dimple, different things like that to indicate the orientation. But you can see here that pin 1 starts here. So it goes like pin 1, 2, 3, 4, 5, 6, oops, sorry, 7, and then it goes across 8, 9, 10 through 14. So every time on an integrated circuit or on a connector as well, these pin orientations matter, and you need to study them and understand them. So, and just to note that this is the typical configuration for this type of integrated circuit, where you start with pin 1, it goes to pin 7, then it goes across to pin 8, and then to pin 14. But if you put it in backwards, you can imagine that 2 of these pins have a ground, another one has a voltage, and you put this thing in backwards, and unfortunately, they don't make these where those are like reversible. So if you put this in backwards and then the voltage and the ground are in 2 different pins that they should be in, you could certainly cause the device will fail.
And it also doesn't help that some chips, depending on the data sheet again, always read your data sheet, will have multiple grounds. And
Yes.
it just takes one of those grounds being connected to power for your chip to be fried.
Yes. So again, they're polarized. It matters which way you install them. Observe the pin 1 location. And then this is really important to treat all ICs as if they are very susceptible to electrostatic damage. And they really are, and rigorous precautions should be taken. And then leads should generally not be bent. And I would say like another kind of safety factor with ICs is that people tend to just like leave them out and turn them upside down, and then you're sitting there working and you just put your arm over it, and they have little pointy leads that go into your arm. They're normally not super sharp, but you know, just like your body part will come into contact with these if you're not really paying attention to where they're located at around your area. So just be careful where you put them at. So how do you protect against ESD? I would say you're always at risk for ESD, even with these precautions, but you can certainly mitigate a lot of that risk with doing simple things. One of them is to ground your work surface, and that means to use an anti-static mat. And I think maybe this is sent. And if it's not sent, if you don't have one or you want one, you can get them really cheap on Amazon. They have them. Just look up anti-static mats. You can get some really small ones that are perfect for your work area. Oftentimes, there will be a wrist strap, or so normally these things will be like a little mat, and then they have a little button on them that you can connect a wrist or ankle strap that will allow you to sort of ground yourself through a series resistor of high value to that mat. And so basically your whole area is grounded. And then, you know, be aware of your tools as well as what's happening around you. And then one of the best ways to do this is to, you know, simply touch a grounded object before handling this to discharge yourself. That's a great, if you know it's a kind of a day where you're touching things and you're especially if you're wearing fleece. Fleece is really bad. Then just make sure you're discharging yourself before you're handling your work area. And this is another activity that we probably won't go into detail here, but you all should inventory the parts supplied to you in your Skeeter SAT kit, and the complete parts list is provided. And then get an understanding of the ESD precautions and how to protect your work area as well as the parts. And then sort the parts into the groups and just go back over them. Look at this on the internet. Type it in. Look at the part numbers like we talked about, and then determine the value and tolerance of each part as appropriate.